In 2004, astronomers pointed their telescopes at a region of space they expected to be filled with thousands of galaxies. They found nothing. Not darkness, not empty space as we understand it. Something far more disturbing. A void so vast, so incomprehensibly empty, that light takes 1 billion years to cross from one side to the other. A region where the cosmic web, the fundamental scaffolding of reality itself, has been torn away, leaving behind a wound in the fabric of existence. This isn't just empty space. Something about this void violates the laws of physics as we know them, something that suggests our universe may be fundamentally unstable, something that hints at forces we've never detected, operating on scales we can barely comprehend. What scientists discovered inside this void challenges everything we thought we knew about how the universe formed, how it evolves, and what its ultimate fate might be. The evidence suggests that empty space isn't empty at all, and what fills it might be the most dangerous thing in the cosmos. Today, we journey through evidence that challenges everything we thought we understood about reality itself. We'll explore why some of the brightest minds in physics believe these cosmic voids might be windows into a hidden structure underlying all of existence, a structure that could spell doom for everything we know. Prepare yourselves. We begin.
August 2007. Lawrence Rudnick and his team at the University of Minnesota were conducting a routine survey of the cosmic microwave background, the afterglow of the Big Bang that permeates all of space. They were mapping temperature variations across the sky, expecting the usual subtle fluctuations that reveal density differences in the early universe. Instead, they found a cold spot. Not just cold, impossibly cold. A region spanning more than 1 billion light-years across, where the cosmic microwave background radiation measured 70 microkelvins colder than the surrounding space. To put that in perspective, that's colder than the coldest natural temperature ever recorded in the universe outside of laboratory conditions. It was like finding a hole in the universe, Rudnick later told reporters. We didn't understand what we were looking at. What they had discovered would come to be known as the CMB cold spot, and when they looked deeper, trying to understand what could create such an anomaly, they found something that shouldn't exist according to our model.
Imagine the universe not as scattered stars and galaxies, but as a vast cosmic web, filaments of matter stretching across billions of light years, with clusters of galaxies at the intersections, like drops of dew on a spider's web. Between these filaments lie voids, regions with relatively few galaxies. We've known about these voids since the 1970s. They're a natural consequence of how matter clumped together after the Big Bang. Dark matter's gravity pulled material into dense regions, leaving empty spaces behind. But the void Rudnick's team had found was different. Subsequent observations revealed a region of space approximately 1.8 billion light-years across, containing 10,000 times less matter than expected. If you could somehow stand at the center of this void and look out in any direction, you would see no galaxies, no stars, no light from distant objects, just emptiness extending further than human comprehension can grasp. To understand how strange this is, consider this. In a typical region of space this size, you'd find roughly 2,000 galaxy clusters. In the supervoid that creates the cold spot, astronomers found fewer than 100. Something had evacuated matter from this region on a scale that our cosmological models said shouldn't be possible. The discovery triggered immediate controversy in the astronomical community. Some scientists argued it was simply a statistical fluke. Look at enough patches of sky, you'll eventually find something unusual. Others suggested instrumental errors or contamination from our own galaxy. But then they found more. In 2013, astronomers identified another massive supervoid in the constellation Eridanus, then another in the direction of Boötes, the Great Nothing as it came to be called, stretching 330 million light-years across. By 2015, teams using data from the Sloan Digital Sky Survey had mapped dozens of these cosmic voids, and a disturbing pattern emerged. They were far larger and far emptier than cosmological simulations predicted they should be. The standard model of cosmic evolution, the Lambda CDM model that has guided our understanding of the universe for decades, predicts that matter should be distributed relatively evenly on the largest scales, with voids no larger than about 300 to 400 million light-years across. Yet here were structures 3, 4, even 6 times larger. And they were cold. The coldness matters. Here's why. When light from the cosmic microwave background travels through space, it gets stretched by the expansion of the universe, a process called redshift. When that light passes through a massive void, something peculiar happens. As photons fall into the void, they gain energy, becoming slightly hotter. As they climb out the other side, they should lose that energy again, becoming colder. In a static universe, these effects would cancel out perfectly. But our universe is expanding, and the expansion is accelerating, driven by something we call dark energy. This means the void is actually expanding while the light passes through it. The photon climbs out of a weaker gravitational well than it fell into. It ends up colder than when it entered, an effect called the integrated Sachs-Wolf effect. Scientists calculated how much colder the cosmic microwave background should appear when passing through even the largest voids predicted by our models. The answer? About 10 to 20 microkelvins at most. The cold spot measured 70 microkelvins colder. Something wasn't adding up. Either our understanding of how the universe expands is fundamentally wrong, or something else, something we haven't detected, is operating inside these voids. András Kovács, a researcher at the Boötes Void University in Hungary, spent years analyzing the supervoids. In 2015, he published a paper that sent shockwaves through the cosmology community. His team had measured the void associated with the cold spot in unprecedented detail. They confirmed it was real, they confirmed it was enormous, and they confirmed something even more disturbing. The void was too empty to have formed naturally. According to every simulation, every model, every theory of structure formation we possess, this much matter shouldn't have been able to evacuate from such a large region in the 13.8 billion years since the Big Bang. The universe simply hasn't existed long enough for gravity to have pulled matter away so completely. We found that it's very unlikely that the cold spot and the supervoid are unrelated, Kovács stated. But we also found that it's very unlikely that standard cosmology can explain them. The discovery created what physicists call an anomaly, an observation that doesn't fit within our current theoretical framework. Anomalies come in two varieties, those that lead to minor adjustments in our theories, and those that signal something fundamentally wrong with our understanding of reality. The question became, which type of anomaly were the supervoids? Some scientists suggested modifications to our cosmological models. Perhaps we had underestimated how quickly structure could form in the early universe. Perhaps dark energy behaved differently than we thought. Perhaps there were subtle effects of general relativity we hadn't properly accounted for. But others began exploring a more radical possibility. What if these voids weren't just empty space? What if they were wounds in reality itself? Places where the quantum fabric underlying our universe had somehow been damaged or transformed? What if they were growing? The more astronomers looked, the more voids they found. And the more they studied them, the stranger they became. But the evidence forces us to confront an uncomfortable possibility. These cosmic voids might not be passive features of the universe's structure. They might be active entities, dynamic, evolving, expanding, and they might be connected to the most destructive force in theoretical physics, a force that could, quite literally, unravel reality itself. The first hint that something more sinister might be occurring came from an unexpected source: gravitational waves. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected ripples in space-time from colliding black holes over 1 billion light-years away. This groundbreaking discovery opened a new window into the universe, allowing us to observe phenomena that emit no light. Scientists immediately began using gravitational wave data to map the large-scale structure of the cosmos, and they noticed something peculiar. When gravitational waves passed through regions of space containing massive galaxy clusters, dense concentrations of matter, they arrived precisely when expected, matching predictions from general relativity. Their frequency and amplitude told us about the distribution of matter they had passed through. But when gravitational waves traveled through supervoid regions, something unexpected happened. A team at the Max Planck Institute for Gravitational Physics analyzed gravitational wave signals that had traversed the supervoid in Eridanus. The waves arrived slightly earlier than predicted, a discrepancy of only milliseconds, but detectable with LIGO's extraordinary precision. More troubling, the waves showed subtle variations in frequency that suggested they had passed through regions of space where the fabric of space-time itself was stretched differently than general relativity predicts. It's as if space-time is thinner inside the voids, explained Dr. Alessandra Buonanno, director of the Institute's Astrophysical and Cosmological Relativity Division. The gravitational waves propagate slightly faster, as if encountering less resistance. This finding aligned with a provocative theory that had been gaining traction in theoretical physics circles, the vacuum instability hypothesis. To understand this hypothesis, we need to talk about the vacuum, what physicists call empty space. You might think of a vacuum as true nothingness, no matter, no energy, no anything. But quantum mechanics tells us something different. Even in the emptiest regions of space, quantum fields permeate everything. These fields constantly fluctuate, creating and annihilating virtual particles in a process that occurs on timescales too brief to measure directly. The energy associated with these quantum fluctuations is what we call vacuum energy. And here's where things get strange. The vacuum can exist in different states, each with different energy levels. Think of it like water. Water can exist as ice, liquid, or steam. Same substance, different states, different energies. The vacuum might be similar. and our entire observable universe might exist in what physicists call a false vacuum, a metastable state that appears stable, but could, under the right conditions, tunnel to a lower energy true vacuum state. If that happened, the consequences would be catastrophic. To understand this hypothesis, we need to talk about the vacuum, what physicists call empty space. You might think of a vacuum as true nothingness, no matter, no energy, no anything. But quantum mechanics tells us something different. Even in the emptiest regions of space, quantum fields permeate everything. These fields constantly fluctuate, creating and annihilating virtual particles in a process that occurs on timescales too brief to measure directly. The energy associated with these quantum fluctuations is what we call vacuum energy. And here's where things get strange. The vacuum can exist in different states, each with different energy levels. Think of it like water. Water can exist as ice, liquid, or steam. Same substance, different states, different energies. The vacuum might be similar, and our entire observable universe might exist in what physicists call a false vacuum, a metastable state that appears stable but could, under the right conditions, tunnel to a lower energy true vacuum state. If that happened, the consequences would be catastrophic. The transition from false vacuum to true vacuum would propagate outward at the speed of light as a bubble of different physical laws. Inside the bubble, the fundamental constants of nature, things like the strength of electromagnetic force or the mass of elementary particles, would change dramatically. Atoms would tear apart. Chemistry as we know it would become impossible. Complex structures like stars, planets, and living beings would cease to exist. The terrifying part? We'd never see it coming. The bubble would travel at light speed, giving us zero warning before the transformation overwrote our region of space. This is called vacuum decay, or vacuum metastability, and it's one of the most unsettling predictions of quantum field theory. Most physicists consider it a remote possibility. If our vacuum is metastable, its lifetime would exceed the current age of the universe by countless orders of magnitude. But what if the cosmic supervoids were evidence that vacuum decay wasn't just theoretical? What if these regions were places where the vacuum had already begun transitioning to a different state? In 2017, a provocative paper appeared in the journal Physical Review D. The authors, a team from the University of Warsaw, proposed that the supervoids could be explained if the vacuum energy inside them was lower than in surrounding space. They calculated that a reduction of just 1 part in 10,000 in the vacuum energy density, a change so small it would be nearly impossible to detect directly, could explain both the excessive size of the supervoids and the unusual coldness of the cosmic microwave background passing through them. The mechanism they proposed was chilling. Perhaps in the early universe, quantum fluctuations in certain regions allowed the vacuum to tunnel to a lower energy state. As the universe expanded, these regions grew into the supervoids we observe today. Not everyone agreed with this interpretation. Critics pointed out that if vacuum decay had occurred in these regions, the effects should be far more dramatic than we observe. The physical constants inside shouldn't be noticeably different. Stars and galaxies inside the voids shouldn't be able to form at all. But then astronomers made another discovery that deepened the mystery. Galaxy surveys revealed that galaxies on the edges of supervoids behaved strangely. They exhibited peculiar motions, velocities that couldn't be explained by the gravitational attraction of visible or dark matter in the region. It was as if something was pushing them away from the voids. The effect was subtle, additional velocities of just a few hundred kilometers per second, but across the millions of galaxies surveyed, the pattern was unmistakable. Galaxies near supervoid boundaries were being accelerated away from the void centers faster than cosmological models predicted. This aligned with what we'd expect if the vacuum energy inside the voids was indeed different from surrounding space. Lower vacuum energy means lower pressure. The quantum vacuum in normal space would push matter away from the low-pressure void region, like air rushing into a vacuum chamber. But this represents just one piece of a much larger puzzle hidden in the structure of space-time itself. The most remarkable discovery involves the relationship between supervoids and dark energy. Dark energy, the mysterious force causing the universe's expansion to accelerate, remains one of the greatest unsolved problems in physics. We know it exists because we can measure its effects. We know it comprises roughly 68% of the total energy content of the universe, but we have no idea what it actually is. The simplest explanation is that dark energy is just the vacuum energy of empty space, a cosmological constant that Einstein himself proposed and then famously called his greatest blunder. But there's a problem with this explanation, and it's one of the most embarrassing failures in theoretical physics. When physicists calculate what the vacuum energy should be based on quantum field theory, they get an answer that's 10 to the 120 times larger than what we observe. That's a 1 followed by 120 zeros, the largest discrepancy between theory and observation in the history of science. This is called the cosmological constant problem, and it stumped physicists for decades. But the supervoids might offer a clue to its solution. In 2019, researchers at the University of Cambridge published a groundbreaking study analyzing the distribution of dark energy around cosmic voids. Using gravitational lensing, the bending of light by massive objects, they could map the dark energy distribution with unprecedented precision. What they found was startling. The dark energy density inside the largest supervoids appeared to be measurably different from the cosmic average. Not by much, only about 3 to 5%, but statistically significant. If confirmed, this would be revolutionary. It would mean dark energy isn't truly constant across space. It varies, and it varies most dramatically inside the supervoids. This suggests that dark energy and vacuum energy are connected in ways we don't fully understand, said Dr. Marco Regis, one of the study's authors. The voids might be regions where we're seeing the quantum structure of space-time revealed. But the evidence extends beyond dark energy into the realm of quantum mechanics itself. In 2021, physicists proposed a radical experiment. Send quantum-entangled particles through a supervoid and measure whether their entanglement behaves differently than in normal space. Quantum entanglement is perhaps the strangest phenomenon in physics. When two particles become entangled, measuring one instantly affects the other, no matter how far apart they are. Einstein called it spooky action at a distance and never fully accepted it, but experiment after experiment has confirmed it's real. The strength of quantum entanglement depends on the structure of space-time. In regions where space-time is highly curved, near black holes for instance, entanglement can be enhanced or degraded in measurable ways. If the vacuum state inside supervoids is different from normal space, as the evidence suggests, then entanglement should behave differently there too. The experiment hasn't been performed yet. Sending quantum particles billions of light years through space isn't exactly feasible with current technology, but theoretical calculations suggest that if we could conduct such an experiment, we'd find that entanglement decays faster inside supervoids. Why? because the quantum fields that carry entanglement information would be in a different state. The fabric of reality itself would be fundamentally altered. Perhaps the most disturbing evidence comes from studies of cosmic microwave background polarization patterns. Light becomes polarized when it scatters off matter. The electromagnetic waves oscillate in preferred directions. The cosmic microwave background shows subtle polarization patterns that tell us about conditions in the early universe. In 2022, the European Space Agency's Planck satellite completed the most detailed map ever made of CMB polarization across the entire sky. When astronomers examined the polarization patterns in the direction of the supervoids, they found anomalies. The patterns were twisted, rotated slightly from what general relativity predicts. The rotation was tiny, just a fraction of a degree, but consistent across multiple supervoid regions. This phenomenon, called cosmic birefringence, occurs when light travels through space with unusual properties. It's exactly what you'd expect if the quantum vacuum inside these regions has different characteristics than normal space. The polarization data suggests that the photons passing through these voids experienced something we don't see in normal space, explained Dr. Eiichiro Komatsu, director of the Max Planck Institute for Astrophysics. Then came the most recent discovery, one that has physicists genuinely concerned. In early 2024, a team analyzing data from the Dark Energy Spectroscopic Instrument noticed something extraordinary. The supervoids are expanding faster than the universe around them. Let me repeat that. The voids aren't just empty regions passively being stretched by cosmic expansion. They're growing at an accelerated rate, pushing matter away from their boundaries like invisible bubbles inflating inside the cosmic web. The team measured the expansion rate of several large voids and found they're growing between 8 and 12% faster than cosmic expansion alone would predict. This excess expansion correlates directly with the void size. Bigger voids expand faster, following a precise mathematical relationship. This is exactly what vacuum decay theory predicts. If a region of space has transitioned to a lower energy vacuum state, it would expand faster than surrounding space. The bubble of altered vacuum would grow, consuming more of the universe over time. The larger the bubble, the faster it expands, because the pressure difference at the boundary becomes more extreme. The evidence extends beyond what we can directly observe into what we can infer about the structure of reality itself. Mathematical models of quantum field theory in expanding universes predict that vacuum fluctuations should occasionally create regions of lower energy vacuum. These would typically be microscopic, smaller than an atom, and would vanish almost instantly. But during cosmic inflation, that brief period in the first fraction of a second after the Big Bang, when the universe expanded exponentially, quantum fluctuations could have been stretched to cosmic scales. Perhaps the supervoids are exactly that, quantum vacuum fluctuations from the moment of creation, preserved and magnified by cosmic expansion, now revealed as massive structural features of the present-day universe. If this interpretation is correct, the voids aren't anomalies, they're fossils, imprints of the quantum uncertainty that existed at the very birth of space-time. And they might be slowly unraveling everything we know.
Act 3. The Big Picture. The scientific theory that ties all these observations together is called the landscape of string theory, though it's far more disturbing than it sounds. String theory proposes that the fundamental constituents of reality aren't point-like particles, but tiny vibrating strings of energy. Different vibration patterns create different particles, electrons, quarks, photons, and everything else.
For decades, physicists hoped string theory would provide a unique description of reality, one set of equations that explained everything. But when mathematicians worked out the full implications, they discovered something shocking. String theory allows for approximately 10 to the 500 different possible vacuum states. That's more possible configurations than there are atoms in the observable universe. Each vacuum state has different physical constants, different particles, different forces. Our universe exists in one of these states, the one that allows matter, stars, galaxies, and life to exist. But it might not be the lowest energy state. We might live in what physicists call a local minimum of the energy landscape, a valley in the quantum terrain that's stable enough to persist for billions of years, but not the deepest valley possible. This is where the supervoids become terrifying. Leonard Susskind, one of the founders of string theory, has spent years studying what happens when a false vacuum region decays to a lower energy state. His calculations suggest that once such a transition begins, it's irreversible and unstoppable. The decay proceeds via quantum tunneling, Susskind explains. A small bubble of true vacuum nucleates somewhere in space, perhaps triggered by a quantum fluctuation, or perhaps spontaneously. That bubble then expands at the speed of light, converting false vacuum to true vacuum as it grows. But here's the crucial insight. Before the bubble expands outward, it must first expand inward into the false vacuum, creating a region of depleted vacuum energy. This region would appear from outside as an expanding void, growing faster than cosmic expansion, with unusual gravitational properties and altered physical constants. In other words, it would look exactly like the supervoids we observe. Not everyone agrees with this interpretation. Alternative theories abound. Some physicists argue the voids are simply statistical flukes, rare but natural outcomes of random structure formation. Others suggest they're evidence of modified gravity theories that alter how matter clumps on the largest scales. Still others propose they're signatures of primordial black holes or other exotic phenomena from the early universe. Yet Dr. Rein van de Weegaert, a leading expert on cosmic voids at the University of Groningen, cautions against jumping to dramatic conclusions. The voids are certainly unusual, he notes, but unusual doesn't necessarily mean dangerous. We're dealing with complex astrophysical phenomena we don't fully understand. It's possible, perhaps even likely, that the explanation lies in some conventional physics we simply haven't properly accounted for yet. Yet he acknowledges, if the voids really do represent regions of altered vacuum energy, that would be the most important discovery in cosmology since the detection of cosmic expansion itself. It would tell us that the fabric of our universe is less stable than we've assumed. This forces us to reconsider fundamental assumptions about the nature of reality. We typically think of physical laws as absolute and unchanging, the same everywhere and every when. The speed of light is constant, the charge of an electron never varies, the strength of gravity remains fixed. But string theory suggests this isn't quite right. Physical laws might be more like local bylaws, rules that apply in our particular vacuum state but could be different elsewhere. The supervoids might be the first observational evidence that we live in a multiverse of different vacuum states, each with its own physics. If that's true, then the voids aren't threatening our reality. They're showing us reality itself is far more variable and dynamic than we imagined. Or perhaps they're both revealing and threatening simultaneously.
Part B. Future implications. Recent breakthroughs suggest we're on the verge of definitively testing whether the supervoids represent vacuum instability. The Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will conduct the most comprehensive survey of large-scale cosmic structure ever attempted.
With a field of view 100 times larger than Hubble's, it will map billions of galaxies and identify thousands of supervoid structures. But more importantly, Roman will measure the gravitational lensing signature of dark energy with unprecedented precision. If dark energy really does vary inside supervoids, as recent evidence suggests, Roman will detect it conclusively. We'll be able to map the dark energy field across the sky at high resolution, explains Dr. Jason Rhodes, a senior research scientist at NASA's Jet Propulsion Laboratory. If supervoids show systematic deviations in dark energy density, we'll know that something fundamental is going on with the vacuum. Meanwhile, the next generation of gravitational wave detectors promises to probe space-time structure directly. The Laser Interferometer Space Antenna, LISA, will launch in the mid-2030s. Unlike LIGO, which sits on Earth's surface, LISA will orbit in space, using 3 spacecraft separated by millions of kilometers to detect gravitational waves from supermassive black hole mergers across cosmic distances. When gravitational waves from these mergers pass through supervoid regions, LISA will measure their propagation properties with extraordinary precision. Any deviation from general relativity's predictions, any hint that space-time itself is structured differently in these regions, will be unmistakable. LISA will essentially give us a tomographic scan of space-time structure across the universe, notes Dr. Karsten Dansman, principal investigator for the LISA mission. We'll be able to see if these voids really do represent regions where the quantum vacuum has different properties. But perhaps the most ambitious proposal involves sending an actual spacecraft to study a void boundary directly. The concept is called Project Void Probe, still just a theoretical mission studied by NASA's Advanced Concepts Division, but surprisingly feasible with near-future technology. A spacecraft equipped with quantum sensors would be sent to the boundary region where a void meets normal space, specifically the relatively nearby void in the direction of Boötes, only about 700 million light-years away. Yes, 700 million light-years is nearby in cosmic terms, but obviously far too distant for any spacecraft we could build. Instead, the mission would use an indirect approach, positioning sensitive instruments at a point where light from a distant quasar passes through the void boundary region before reaching us. By analyzing the quantum properties of that light, looking for subtle signatures of vacuum variation, scientists could detect if the photons have interacted with a different vacuum state. We're essentially using the distant quasar as a probe, explains Dr. René Hlojek, a cosmologist at the University of Toronto working on the concept. Its light passes through the void boundary for us. We just need to analyze what that light tells us about the journey. What these future observations might reveal has profound implications for humanity's long-term future. If the voids are indeed regions of altered vacuum energy, and if they're expanding, then we face a cosmological timescale threat. Not imminent, not even in the next million years, but eventual. These bubbles of different vacuum might expand to consume the entire observable universe. The timescale matters. If the expansion continues at current rates, the nearest supervoid boundary would reach our galaxy in approximately 50 billion years, long after the Sun has exhausted its fuel and Earth has become uninhabitable for other reasons. But there's an unsettling uncertainty. Vacuum decay might not proceed at constant speed. Theoretical models suggest the expansion could accelerate, slowly at first, then faster. A phase transition could occur when the voids reach a critical size, causing them to suddenly expand much more rapidly. We're dealing with quantum processes scaled up to cosmic dimensions, notes Dr. Catherine Fries, director of the Weinberg Institute for Theoretical Physics at the University of Texas. Our understanding of how such processes evolve over cosmological timescales is still very limited. We can't rule out the possibility of sudden, dramatic changes in the expansion rate. What this means for us comes down to a profound question about the nature of existence itself. Are we living in a stable, eternal universe where the laws of physics are fixed and unchanging? Or are we inhabiting a temporary island of stability in a vast ocean of quantum uncertainty? A metastable bubble that will eventually transform into something unrecognizable. The supervoids might be showing us the answer, and that answer might be that reality itself has an expiration date. Not soon, not catastrophically imminent, but eventual, inevitable. The universe as we know it might be temporary.
Act 4. The Ultimate Questions. The most profound implications emerge when we consider what the supervoids tell us about consciousness, meaning, and our place in the cosmos. If the fabric of reality is indeed metastable, if the physical laws that govern our existence could transform given enough time, then everything we've built, everything we've learned, everything we've become as a species might ultimately be erased, not by entropy or the heat death of the universe, but by a transformation of reality itself into something where atoms, molecules, and living beings cannot exist. This raises what philosophers call the existential risk of vacuum decay. Unlike other cosmic threats, asteroid impacts, supernovae, even black holes, vacuum decay would obliterate not just our physical structures, but the very possibility of structure. It would be, quite literally, the end of meaning itself. But perhaps the most mind-bending implication is this: we might not be the first. If our universe has existed for 13.8 billion years in a metastable vacuum state, and if that state has been decaying in scattered regions throughout cosmic history, then perhaps other civilizations have already encountered expanding void boundaries. Advanced civilizations, far more advanced than ours, might have detected the approach of vacuum decay and attempted to escape it or prevent it. They might have developed technologies to stabilize the quantum vacuum or to flee into pocket universes with more stable vacuum states. Or they might have failed. The Fermi paradox asks, if the universe is vast and old, where are all the aliens? One of the more disturbing proposed solutions is the Great Filter, some challenge so difficult that virtually no civilization survives it. Could vacuum instability be that filter? Perhaps the silence we detect when we search for extraterrestrial intelligence isn't because intelligent life is rare. Perhaps it's because intelligence eventually discovers the instability of reality itself, and that discovery comes too late. The most disturbing evidence comes from recent analysis of galaxy formation patterns around the largest voids. These patterns suggest that galaxy formation ceased in void boundary regions about 2 to 3 billion years ago, much earlier than in normal space. If civilizations had emerged on planets orbiting stars in those boundary regions, they would have watched their night sky gradually empty as nearby galaxies receded into the expanding void. They would have measured the accelerating expansion. They would have calculated when their own galaxy would be consumed. What would they have done with that knowledge? We don't know. We can't know, because if they existed, they're gone now. Not destroyed by war or ecological collapse or any conventional catastrophe, but by the dissolution of space-time itself. Yet there's a strange paradox buried in the mathematics of vacuum decay that offers a peculiar kind of hope. Quantum mechanics is fundamentally probabilistic. The wave function never collapses to absolute certainty. There's always some residual probability, no matter how small, that a quantum system will be found in an unexpected state.
Applied to vacuum decay, this means that even inside a region where the vacuum has transitioned to a lower energy state, there's always some infinitesimal probability that quantum fluctuations will recreate pockets of the original vacuum. These pockets would be microscopic and fleeting, but they would exist. And if they exist, then, given infinite time, there's a non-zero probability that one of these quantum fluctuations will be large enough and stable enough to generate a new universe. A bubble within the bubble. A resurrection of structure and possibility inside the void. The universe might be self-healing, suggests Dr. Alan Guth, the MIT physicist who first proposed cosmic inflation. Vacuum decay could destroy a region of space, but quantum mechanics could recreate it. Not the same universe, the physical constants would be different, but a universe. The possibility of existence would persist. This leads to an even stranger thought. Perhaps our universe itself is one of these quantum resurrections. Perhaps the Big Bang wasn't the beginning of everything, but the rebirth of space-time inside a region of altered vacuum. Perhaps the supervoids we detect are echoes of the previous universe, wounds not yet healed, scars of a catastrophe that already occurred. What the evidence ultimately suggests about reality itself defies easy summarization. The supervoids show us that space is not empty, that vacuum is not nothing, that the stage on which cosmic drama unfolds is itself a dynamic, evolving entity, one that can transform, decay, and perhaps even regenerate. They reveal that the universe is far stranger than we imagined, not a static arena of fixed laws, but a constantly shifting landscape of quantum possibilities where the very fabric of existence can tear and reform. They remind us that we live in a tiny island of stability within an immense ocean of quantum chaos, an island whose shores are slowly being eroded by forces we're only beginning to understand. And they pose a question that each generation of humanity must answer for itself. Knowing that everything we build might ultimately be temporary, does meaning evaporate? Or does it become more precious precisely because it's finite?
We began this journey by asking what astronomers found when they pointed their telescopes at a region of space they expected to be filled with galaxies. Now we understand. They found evidence that reality itself is less stable than we assumed, that the laws of physics that feel eternal might be temporary, that the universe is not a fixed stage, but an evolving story, one whose ending might involve the dissolution of everything we know. But perhaps that's not the right way to think about it. The supervoids teach us that even apparent nothingness contains extraordinary richness. The empty spaces between galaxies aren't truly empty. They're filled with quantum fields, dark energy, and the constantly fluctuating fabric of space-time itself. These voids aren't the absence of reality, they're reality revealing its quantum nature. The current scientific consensus is cautious. Yes, the supervoids are unusual. Yes, they pose challenges to our cosmological models. Yes, they might represent regions of altered vacuum energy, but we need more data before drawing definitive conclusions. The Nancy Grace Roman Telescope will provide that data. LISA will probe space-time structure directly. Future experiments will test whether the quantum vacuum really does vary across cosmic distances. Within the next decade, we'll know whether the voids represent the most important cosmological discovery since Hubble detected the expansion of the universe, or whether they're simply rare but conventional structures that our models haven't properly accounted for. Either answer will transform our understanding. But regardless of what future observations reveal, the supervoids have already given us something invaluable,
a reminder of how much we still don't understand about the universe we inhabit. They stand as monuments to cosmic mystery, billion light-year-wide question marks suspended in the darkness between galaxies, challenging us to look deeper, to question our assumptions, to accept that reality might be far stranger than our theories suggest. We are creatures who evolved to hunt prey on African savannas, somehow finding ourselves capable of detecting quantum fluctuations from the birth of the universe. We've built instruments that can measure the shape of space-time across billions of light years. We've developed mathematics sophisticated enough to describe the behavior of universes we'll never see. And yet, the cosmos continues to surprise us. The darkness holds secrets we're only beginning to glimpse. The voids remind us that the universe is vast, the mysteries are endless, and the journey, this magnificent, terrifying, awe-inspiring journey through the cosmic unknown, continues.